Hey guys, today's video is 6.5 Energy of Phase Changes. Go ahead and pause the video to put this learning target into your own words. Alright, once you have that, we can go ahead and look at this phase change diagram. This is showing you guys a phase change diagram going from solid to liquid to gas, and this is our heating curve. Okay, so as you add heat to a solid that is liquefying, once it starts liquefying at this very first curve here, this is where we are going to see our change in state. Okay, and that's right here. So the temperature is not going to change once it starts to liquefy until all of that solid has completely liquefied. Once it's liquefied, or while it's liquefying, the internal energy of the system is increasing, but the temperature is not, because that energy is actually being used to stretch the attractions from the intermolecular forces. The heat required to liquefy 1 mole of substance is called the heat of fusion, okay, or the enthalpy of fusion. For water, this of course we know is 0 degrees Celsius. Then it's going to continue to warm as a liquid until it reaches, for water, 100 degrees Celsius, and then it reaches its heat or enthalpy of vaporization. When it reaches its boiling point, it's going to stay the same temperature, that's right here, it's going to stay that same temperature until all of the liquid is vaporized. The heat that's being injected into the system is here being used to sever the attractions, because we know when it's liquid and it's changing to gas, those intermolecular forces are now completely coming apart. And when those are all severed and it goes completely from liquid to gas, then the temperature can start increasing again. And that again, we call it the enthalpy of vaporization. All right, so here, this energy must be added to a system in order for solid to liquid or a liquid to gas phase change to occur. That's when we are either melting or boiling. Okay, and the energy of the system in that case increases. Energy has to be released from a system in order for a gas to liquid or liquid to solid phase change to occur. This is when we're freezing or condensing something. And then the energy decreases. All right, so with phase changes and temperature of pure substances here, so we have to add heat in order for a solid to liquid phase change occur, but we just said this. The temperature of the system doesn't change during the process. So you can go ahead and pause here. I've said all this already, but this is just written so that in case you need to go ahead and copy this down, you're welcome to here. So this is a cooling curve, so this is going backwards from the heating curve we just saw. The same thing though is going to happen at those phase change points where when it goes from a liquid to a solid, we don't have any temperature change. We only have that the phase change there. We also have this supercooling that occurs right here. Some liquids supercool before they solidify, and at this bottom temperature here, at the bottom of that supercooling curve, the solid crystals form, causes a drastic increase in temperature, and heat is released, and that's just like serious endothermic reaction. Oh my goodness. Yeah, I'm getting all kind of crazy recorded stuff because I don't want to pause because the music will sound crazy if I do that. All right, so solids here. This is a solid. In this diagram, this is polar molecules in a solid state. We know that they line up in a regular pattern where we have our negatives here sitting next to our positives. That's how they're going to line up. We have dipole-dipole attractions. That is the only one that's formed, like we can only draw our dipole-dipoles, but we have London dispersion here existing. That's in every molecule is going to have our London dispersion. This also has a stronger dipole-dipole. So, and this is our solid. So what we're trying to do here is melt our solid, going from solid to liquid. We just talked about that being our enthalpy of fusion. So when that occurs, the heat is absorbed. Remember, the enthalpy of fusion is the heat absorbed as 1 mole of solid liquefies. the energy required is going to expand or stretch out those bonds that are in between the molecules, those negative and positive, in order for it to stretch out and become a liquid. So molar heat of fusion values are always going to be positive because energy is required. That way melting is always going to be an endothermic process. So the heat of fusion for ionic compounds is always going to be higher than that of the heat of fusion for anything that is polar or nonpolar. That's because we know that our ionic bonds are a lot stronger. That means it's going to take a lot more energy for that to occur. So you'll see here, this is really important. At 0 degrees Celsius, the quantity of heat that flows out of 1 mole of liquid as it solidifies, it's going to be equal to the quantity of heat that flows into 1 mole of ice as it melts. So you'll notice here that the actual quantity is the same, but the sign changes. And we've talked about that a lot. So that the endothermic and exothermic reactions of the same substance, the actual quantity is going to be the same. It's just that the sign is going to change because in one, heat's going in and the other, heat is going out. This is a pictorial way to represent that. So you see that heat is going in the heat of fusion, and in the heat of vaporization, heat is going out. Okay, for liquids, with the same intermolecular forces are going to exist, but they're just not as strong as they might be in a solid. Ideally, if we have this in a gaseous state, there's actually no intermolecular forces whatsoever. Of course, we know there is a little bit because at some point they are going to get together. But in an ideal gas, there are no intermolecular forces. So enthalpy of vaporization, that is when we're talking about our liquid going to a gaseous phase. So in this particular case, energy is required to sever those intermolecular forces of attraction. That is vaporization. So it's always going to be endothermic and it's always going to be positive because you have to add energy in this particular case. Again, same thing we just talked about, vaporizing and condensing are opposite phase changes. So our quantity, our number, the magnitude is going to be equal, but they're just going to be opposite charges. Because one, you have to put energy in, the other one, you are actually releasing energy. Another way to look at it with the energy diagram. Okay, last one we want to talk about is sublimation. Okay, sublimation is when solids evaporate directly solids evaporate directly into gases. These have actually a very high vapor pressure. So two things that do this that are just common substances are mothballs. That's naphthalene, mothballs. That's why they have a really strong smell, because the vapor given off is the sublimation. And then solid carbon dioxide or dry ice, it sublimes at 25 degrees Celsius and 1 atm. So just the heat of sublimation is equal to the heat of fusion plus the heat of vaporization. The energy required to sublime 1 mole of solid is equal to the energy required to liquefy, which is our heat of fusion, and then vaporize, which is our heat or enthalpy of vaporization, 1 mole of that substance, and that just happens at the same time. Okay. Ionic compounds have very low vapor pressures. They have really strong Coulombic attractions between the cations and the anions. Because they have such strong intermolecular forces, they have low vapor pressures. So you just need to know the stronger the Coulombic attraction is between the molecules, the lower the vapor pressure is going to be. Okay, that means it's going to take more energy in order for the bonds to first stretch and then break. Okay, and here is just an example of the enthalpy of sublimation, and then a pictorial representation of your enthalpy of sublimation. All right, we will do some practice problems in class. Y'all have a good afternoon.